I'll try to explain what zero-knowledge proofs are and maybe why they're also useful. Well, we can start with a proof. Proof is the basis of mathematics. The way we know that something is absolutely true is by proving it. Like, we know that every sum of angles in every triangle is 180 degrees, and we can prove it. And then we know that this is true for every triangle we meet, even some we didn't meet. Proofs are what makes us certain about certain mathematical facts. What makes us certain about it is that they are convincing. They follow this logic that any person who wants to verify the proof can just follow the steps of the proof and be convinced that it is indeed true. To someone who didn't know it was true in advance, let's call this guy a verifier of the proof. There's a way to check, even if he didn't know a proof, to check, given a proof, that it's correct. And usually it's much simpler than proving a theorem, right? The prover, the guy who proved it, may be a genius, one in lifetime, like Wiles, who proved Fermat's last theorem. But once he did it, he wrote down a proof, and then people, maybe with some amount of work, but not much need for ingenuity, could verify that it's correct. So that's a proof. So what are zero-knowledge proofs? Zero-knowledge proofs, by the name, they are proofs that reveal absolutely no information to the verifier. So again, we have a prover who knows some truth and some proof of it, maybe a mathematical theorem. There is some verifier. Someone would want to maybe be convinced of that truth, but would not be fooled by any nonsense. So it's the process in a zero-knowledge proof should be convincing on the one hand, if the claim is true, should not be convincing if the claim is false, or if I don't have a proof for it. So let's say it's me and you, I want to convince you. This conversation between us, at the end of it, you know nothing more than you knew before, except that the claim I made was true. There is no information about the proof in this conversation. There is no information about anything, in fact, that you didn't know. And nevertheless, there is no way to fool you, and there is no, and you will be convinced. I cannot trick you into believing something incorrect or something I don't have a proof of.
You say that after you've convinced me I have no new information.
Yeah. Except
for the information that X, Y, Z is true?
Yeah, so maybe let's give an example, maybe. It's a story I like to tell, even though it seems like mathematicians may be paranoid. So it's you and I again, but say I'm a junior math professor and you are my chairman. And maybe we are both number theorists. And I come to you and say, look, I just proved the Riemann hypothesis. So for the audience, this is maybe the most famous problem in mathematics.
It's the Holy Grail.
And the Holy Grail, yeah. And I come to you and I say, look, I proved it. Can I get tenure? And you say, sure, if you did, show me how the proof goes, You are also a number theory. So, I mean, in a normal conversation between mathematicians, I'll start using the board or your brown paper or something, and, start showing you the lemmas and their proofs and the whole sequence. Maybe it will take an hour, maybe it will take a day, or maybe it will take a year. But, if I had the proof, you'll be convinced. And what's the problem in this process? I mean, there's no problem. That's how mathematicians work. But there are a few stories in the history of mathematics, some of which you may know, that it didn't end quite as well, where the senior guy, having heard the proof, rushed and published it.
Stole it.
Yes. There, so it happened. It's not that I say it happened often, but it happened. So maybe the junior guy, me, would like some protection. It would be much better for me if I could convince you completely that I have a proof, I know a proof of the Riemann hypothesis, without giving you a shred of evidence besides, that it's true. Right. So that's value for a zero-knowledge proof. So that's an example. So now you should ask yourself which mathematical statements or which statements at all have such proofs. Maybe some do, maybe none do. Maybe it seems counterintuitive to say the least, because we somehow associate conviction with information transfer. I mean, there's nothing. If I didn't learn anything new and I didn't know this was true, It's another example. Suppose that we are both faced with some Sudoku puzzle. Somehow it's too hard for you, but I know how to solve it. And I tell you, look, Brady, I can do this one. And you say, I don't believe you. All right, so one, proof in this case is very simple, right? It's something I just fill in the blanks, you check them. It's a very simple type of proofs. There's a way for me to convince you completely that I can do it without, writing anything in this. It's a different process.
So I don't know your algorithm, but I know you were telling the truth.
You don't know the algorithm. You don't know what's in the. You don't know anything that you knew before. Except that you now believe me that I can fill it up, and we are talking about finite objects. So the proof that the Sudoku thing I can solve it is just the filling of the numbers. Proof that there are infinitely many primes, I can write one down. If I had a proof for the Riemann hypothesis, I expect it would be finite and I could publish it, right? So as I said, you can ask yourself what kind of statements at all can have such proofs. So this question was raised in the context of cryptography by Goldwasser, Micali, and Rakov in the mid-80s. About a year later, Oded Goldreich and Silvio Micali, we proved that every statement which has a proof has a zero-knowledge proof. Okay, every. So we can do it with Sudoku, we can do it with the Riemann hypothesis. Every statement which has a proof also has a zero-knowledge proof. But I just want to say that this zero-knowledge proof will be slightly different than the, so in a normal proof, you just write it down. In a zero-knowledge proof, we need to interact. You need to ask me questions, and, it's an interaction. Okay, so zero-knowledge proofs are interactive.
How can I possibly interact with you without increasing my knowledge?
There are two separate questions. First of all, you can interact with me and I can refuse to answer any question you like, and then you will get no knowledge. Giving proofs in an interactive setting is also, natural. You say, oh, explain this to me, I didn't get it. Or show me an example or whatever. So interactive proofs is a natural object. How do we even prove that something gave no information? I mean, you can wonder about that. How can one prove such a statement? And the way to prove such a statement is that somebody else who has no knowledge of the proof could have generated the conversation we just had. If somebody, or you yourself could have generated the conversation we had. If you yourself could have generated the conversation we had, you didn't need me. Only you, the knowledge, the truth of the statement, could have generated the conversation we had. If you could, that means you learn nothing. So that's how you prove that something is zero knowledge. The way we prove that every statement has a zero knowledge proof was in two parts. First, we proved that a certain type of statements, which is very pictorial, has a zero knowledge proof. Okay, this is statements about coloring maps, which is, relates to the famous problem.
Four color
theorem, so maybe I'll mention it. So we proved that this type of statements about the ability to color maps has a zero knowledge proof. Okay, if you have a proof, it has a zero knowledge proof. And then we appealed to a general result about the NP completeness of this problem. I may talk about this. It's a very important concept in computational complexity. To derive from that every statement which has a proof has a zero knowledge proof. So let me explain about map coloring. Some map, this is a map, like in geographical map, and you can think of what we see are countries. So you'd like to color the countries so that things that are neighboring will have different colors. So maybe we color this one blue. If we color this blue, it means that we cannot color any of these guys blue, so maybe we'll color this one red, and this we cannot color red and blue, so this has to be somehow colored green. I guess this has to be colored red. Let's see if we can do it with three colors. Yeah, I guess this we can color red as well, right? So only countries which share a boundary, a border, cannot be colored with the same color. And then we can, I guess, color this green or blue, whatever you like. So this particular map can be colored with three colors. It's a very famous theorem in mathematics that every planar map, like this one, can, no matter how many countries it has, can be colored with four colors. Or if I need to convince you that I can color a planar map with four colors, you don't need any convincing. You know that there is a paper doing this for any planar map. However, not every planar map can be colored with 3 colors. This is a map. Yeah, so this is also a country. Okay, so we have 4 countries. And they all touch each other. They all have borders with each other. So this needs 4 colors. Not every map can be colored by 3 colors. So now it's an interesting thing to prove. You know, I claim that some map can be colored in 3 colors. Right? Suppose I make this claim. You don't trust me. Say I want a proof. Okay, I can give you the 3 coloring like I gave it here. Right? Say, oh, that's right. I mean, you check the boundaries and say, okay, yeah, that's legit. I believe you. And the challenge is to provide, now the challenge is to provide the zero knowledge proof. So the first part of our paper shows that claims of this type, this map is 3 colorable, has zero knowledge proof.
But the only way I can see that you could prove that is just by doing it, by demonstrating it, by performing the act.
That's right. So that's not the only way.
Right.
It's not the only way. Let's draw again the same map. So I want to convince you that I know how to color this map. And instead of telling you the colors, which would reveal information that I don't want to reveal, I instead, maybe these countries also have numbers. And here, instead of writing down the color for you or painting it, I will put an envelope. Okay, so I tell you, Brady, this map is 3 colorable, and I have a 3 coloring for it. And here is my proof. I put the color I need for each country inside this envelope. Each envelope is like a commitment. Once I put it on the table, and they are real envelopes, think of it as real envelopes. I mean, if we had them, I can do it. They are real envelopes. And inside each is the name of the color I'm going to use for this country.
So if I open an envelope, it will say red or blue? Or...
Yeah, and yeah. So first of all, if you open an envelope, let's say the promise is not only that it's 3 colored, but it's 3 colored with these colors. Red, green, and blue. So if you open an envelope and you see purple, you throw me away. You say, I don't believe you, right? Again, a normal proof would be like, I open all envelopes for you, but that will reveal the coloring. What will happen in the process of proof? I will only let you ask me, Avi, you know, I don't believe you. So maybe, you know, I see that countries 1 and 4 are neighboring. I challenge you, open envelope 1 and envelope 4. And I open them. And, you know, again, if you see a color that's not red, green, or blue, you throw me away. Also, if you see the same color in both, you throw me away. You say, I don't believe you, and the process ends. But, you know, it's possible, and it will be, if I had the proof and we did it, you know, I was not trying to cheat you, that you'll see 2 different colors. Of course, this alone should not convince you very much that, you know, maybe the map has 1 million countries.
You could have just gotten lucky.
I could have been lucky, yeah. And, yeah, so you want to be convinced 99.99999% that I cannot cheat you. 100%, as I say often, we don't have in our world. So, in fact, in this sense, it's not completely like a mathematics, like ironclad, as you mentioned before. You can achieve as high, you know, confidence in the verification as you want, and it will be as close to 100% as you want just by repeating this process, but it will never be 100%. Anyway, so then you can do it again. So because you want to gain confidence, you do it again, and I open again. And then you do it again, I open again. We do it as long as you like. This cannot be it, right? Because if I really put in these envelopes the coloring that I had in mind, then you will eventually have opened all of them and learned everything. So here is the trick. After you looked at 2 envelopes of 2 neighboring countries, I, you know, put a different coloring in, okay?
Same map, different coloring? Or
same map, different color. I'll explain in which way it's different. But yeah, since I have a coloring, you don't believe that there is any coloring, right? I put a different coloring in. Then you test me on some 2 other, yeah, and then the process continues. So now it's not clear why it should be convincing, right? Because I put a different coloring in. And also, it's still not clear why it gives no information, because it's not clear why. Maybe there's only 1 coloring. Maybe. There are maps with one coloring.
Yeah.
So I have to explain to you how both are done. So now I want to convince you the way I'll do it will reveal no information to you. Okay, and for this, I have to explain how do I recolor, how do I fill the envelopes again and again with new colors. It's enough if I do it in a map of just 2 countries. Suppose this is a map. You know, it's part of a bigger map. It's part of a bigger map. Okay, so there are many more countries, but we will focus on 2 because you are going to quiz me on 2. And suppose I had some coloring of this map, and in particular, this was green and this was blue. And otherwise, there were, you know, some blues here, and reds, you know, and
all
other,
sorts.
all sorts, and so on. If I have any 3 coloring of a map, 1, then I automatically have 6. Why? I can always rename the colors, right? I mean, I can, you know, right. Green, right?
Yeah, like you could invert it.
Yeah, maybe I'll just do it. Yeah, I could. Yeah, I can permute them. If I have this coloring, then I also have, you know, what I can just rename the colors, and I call this green, and this red, and this blue, and yeah, maybe I'll do all 6. I don't know. So if I had 1 coloring, I had 6 colorings because I just renamed I can rename the. So the way I'm going to fill the envelopes each round is by randomly picking 1 of these patterns and using it. So if I had 1, I had 6. Now look what will happen to a particular pair that you might quiz me on, right? In 1 coloring, it may have been green and blue. But if you look at, you know, green and blue here, and you see what happens with random renaming, everything is possible and equally likely if I pick it randomly, right? So the point is that in this process, if I had a proof, you will not only see 2 different colors here, you'll see 2 random different colors. You'll see just a random pair from this column. But it's something you could have done yourself. You don't need me for this. If I had a proof, you will learn nothing because the process will just reveal pairs of random colors. If I didn't have a proof, you would catch me cheating. That's it. If we talk also about Andrew Weil's paper, how would I convert that to the zero-knowledge proof? It turns out that the answer to both questions is the same. And the answer is NP completeness. It's one type of question that captures all mathematical statements. So one particular and very favorite NP-complete problem is the problem, does a map have a 3 coloring? What do I mean by capture all mathematical statements? If we have any mathematical statements, let's say the Fermat's last theorem, or that this number is a product of 2 primes, or the 4-color theorem, any statement, also false statements. Maybe there are finitely many primes, or the sum of angles in a triangle is 170 degrees. These are false statements, but any formal mathematical statement can be converted into a map. And I should stress, this conversion is efficient. There is a simple algorithm known to all. It's a result from the late 70s, the fundamental results independently by Cook in the West and Levin in the East. They basically prove that any mathematical statement of the type we just described, well, any mathematical statement that's formal, can be written down, can be converted into a map. And this translation between the statement, any statement, to a map is very simple, efficient, known to everybody. All right? So that's the first part of their. And what do you want of this translation? You want 2 things. That if the statement is, well, we want 3 things actually, but let's start with 2, which are the most obvious one. We want that if the statement is true, the map is 3-colorable. And if the statement is false, the map is not 3-colorable. So at this point, we can translate any statement to a statement about the 3-colorability of maps. This result of Cook and Levin has an additional property, which is very important. If on top of the statement, I had the proof of the statement, the same algorithm that translates it to a map will also provide the 3 coloring of that map. If it was a true statement and I had the proof of it, not only would I give you a map, but I would also know a three coloring of it. Okay, so there are these three properties. I hope it's clear now that if Wiles wanted to prove to you in zero knowledge that he has a proof of Fermat's last theorem, he could do it because he could translate, you could both build a map because you know also the process. Just from the statement you could build a map. So now the truth of the Fermat's last theorem became that the three colorability of this map, that it's the map of the of Fermat, right? It's the Fermat map. And then he would prove you using what the envelopes I just showed, he would prove to you that it's three colorable, and this is an equivalent statement. And if you learn nothing from this, you learn nothing at all.
This process you're telling me about from the 1970s, was it, where you can convert
NP completeness?
NP completeness. It's almost like you can take any proof to it and like show it to a secret third party, and they'll just give you a token that says, "Yeah, you proved it." Like, and then you can just come and show me the token. Yeah, I've got the token, which means I proved it.
No. I mean, you still have to be sure that, we just translated Fermat to three coloring of map, but you still would like to, see the coloring. It's not, we don't trust anybody in this business, right? I mean, the verifier does not trust,
we trust that algorithm. We trust the algorithm that creates the
but
map.
you don't need to trust it. The proof is very simple. You can read it. I mean, it's just we teach it to undergrads, and you can teach it in high schools. This is a very, very simple statement. It's an extremely powerful statement, but it's a fundamental result. It's an absolutely cornerstone of my field. But this does not require trust. Okay, so things we've seen proofs of, we don't require trust. And this we've seen, so it's a simple statement.
It's going through that filter of NP completeness.
Yes.
That gives us the ability to do this. That's like our...
Well, I possibly could have done a trick with envelopes directly on Wiles' paper. I mean, I could. It would be less colorful. I could have done one directly on the product of two primes. I could have done one, but it's this concept of NP completeness is extremely powerful, and I'm not going to get into. Well, I mean, it's my favorite topic also.
So coming back to the product of two primes, when Avi's cryptography business came to Brady and said, "I want you to use me as my business, and I promise you, I'm always multiplying two primes," and I said to you, "Prove it to me without giving away your industry secrets." What would you have done?
I would translate it to a map and given you a zero knowledge proof that this map is three colorable. And you would know that this is an equivalent statement to the statement that I have two prime numbers which multiply to this.
But you would still have to do the zero knowledge on the map. You couldn't just show me the map colored with three colors and said, "Look, see, the map's three colored." And
But that will reveal information. In fact, the coloring will tell you the primes.
Right.
Yeah. You don't want that. You want, I mean, the whole point is that you will learn nothing from the process. If you know the coloring of a three-colored map that you didn't, before.
The three-colored map here that we're creating from all our different proofs, from Andrew Wiles, from our primes, that's an analogy, is it? Or is it? Is it actual?
No. Yeah, absolutely. Yeah, it's real. I mean, the maps will probably be humongous. Will have million or zillion countries in it. At this point, I'm not suggesting it as an efficient process, although people have worked and made efficient versions of it. As like I said, with digital currencies, it seems like it will be, will be commercially available for some purposes. Absolutely, it can be used, but it will not be used for mathematical theorems. Actually, if you think about it. The way mathematical proofs are written, they are not completely formal, right? They use English words. They say, in a similar manner, we also deduce this, or we refer to another paper. Either read it or don't read it. So they have black boxes that are not filled and, may have some errors. Or anyway, you don't necessarily read. Formal proofs are proofs with symbols, like, first-order logic. It's just pure symbols from the axioms. You state the axioms in the beginning, and then you go through the chain of deductions. If Wiles wrote this paper in this language, which that's what you would like to, then it would not be 500 pages as it is now, or 300 pages, it will be 1,000,000 pages. And it is this type of formal proofs that would be converted to maps, right? You need to be formal about it, right? So that's not the usual purpose of zero-knowledge proofs. Their main purpose is in cryptography, and but I would say, sort of intellectually, or for it's sort of like an amazing thing. It's an impossible thing that cryptography can do, and it's just one of many, many, many impossible things. You probably know about digital signatures and playing poker over the telephone, or maybe you don't, or or digital currencies, or elections, electronic elections. Lots of these things, are sort of impossible in a normal world, and you need the axioms of cryptography and know-how of cryptography to make them work. Zero knowledge is one example. It's a favorite example because it's so striking that it's possible at all. This NP completeness is a fundamental point. It allows you, when you want to prove a theorem like zero knowledge proof for every statement, and actually it occurs in many other situations in complexity theory. Having a particular problem with nice properties that captures all other problems is very convenient. You notice that in what I just showed you, the zero knowledge proof for coloring maps, I used properties of maps and I used properties of colorings. This is not available in the Fermat theorem. It's not available in multiplication of primes. So having an NP completeness, having an NP complete problem so elegant, so nice, and so combinatorially convenient was essential for us to devise this proof.
So it's like a mathematical lingua franca, in a way.
Yes, it's a language. It's a language which is extremely useful for demonstrating things that in another context look impossible. The main use of NP completeness is just a demonstration of difficulty of this problem. Basically what it says, it captures all other problems. It captures lots of problems, lots of optimization problems. So we just showed that finding 3 colorings of maps is as hard as proving mathematical theorems in general. If you had an efficient way of 3 coloring maps, you would not need wires for Fermat, right? You could just you translate in the same way and run your algorithm. So NP-complete problems are problems which are expected to be difficult. The P versus NP question, the major question of computer science, is about does every such problem has an efficient algorithm. So in particular, it can be asked: does proving mathematical theorem, let's say within some limit of number of pages, is easy or not? We don't know that it's hard. It's possible. It's quite possible that there's a really simple algorithm that you feed it a statement like Fermat, and in a second it spits out the answer. It's true and even provides the proof. That's the P versus NP question.
But you told me already that every proof can be converted.
I said that if you had a proof for a mathematical statement, well, I told you 2 things. Every statement could be converted to a map in a way that preserves truth. So it just says that 3 coloring maps captures every mathematical statement, right? So for this reason, proving mathematical theorems in general is as hard and as easy as just 3 coloring maps. We don't know whether it's hard or easy, we just know. I also showed you that if I have a proof for a mathematical statement, it can be translated to a 3 coloring of maps.
So any statement becomes a map, and if it's a proof, it's a coloring.
Yeah, if the statement is true, any proof of that statement becomes a 3 coloring of that map.
So if I made a false statement, 170 degrees in a triangle, yeah, I would get a map, but my coloring would be
there will be there will be no coloring, no legal coloring. Yeah. Absolutely, yeah. Like there is no proof, no legal coloring. It's a one-to-one translation. Yeah.
That's an amazing machine.
It's an amazing machine. This is NP completeness. It is an amazing machine. It's like the fundamental, yeah. Again, the Cook-Levin theorem. It's from 70.
What does this machine look like? Like, what does this algorithm look like? Is it like a big Like, is it just a theoretical thing at the moment, or
No,
is there an
no,
actual
it's completely
equation?
yeah, no, it's practical. No, it's an algorithm. It's not an equation. It's an algorithm. It's an algorithm. It gives the first NP completeness result. So it proves that some problem, not this problem.
Is there like an online calculator or a program that you can go and put your statement or proof into and press a button and it spits out?
Yeah, it is. Yeah, you could program it and it will be easy. Yeah, it's easy to program and it's easy to understand. But I'll tell you something about its nature or what it relies on. I mean, in order to have any result of this type, you have to understand what are mathematical statements, what are proofs of mathematical statements, what is the verification process of a normal proof. And the first thing to realize is that verification is central, is not the proof, but the verification of proof that is the main aspect of, mathematics.
And here the verification was me opening the envelopes.
Or even before, just you checking the colors if it's open, right? Forget the zero knowledges, yeah. So the verification process in any proof system in mathematics is simply an efficient computation. It's a computation. You check that colors are different, and if it's written logically, you check that, if we proved A and we proved A implies B, we also proved B. These kind of things they're all local, simple things.
But I'm thinking of this as a very simple thing, but presumably in reality, these maps are ginormous.
But doesn't matter.
And even spotting two coloured countries together might be hard to spot? Or?
No, but you pick two, you just pick two countries. I mean, it's very simple. I mean, even if it has a zillion countries, I pick, 100,000 and 273 and another one. If they are not neighboring, I'm not going to answer you, but if they are neighboring, I'll open them. It's simple. It's simple even if it's a large number. You just have to pick randomly the two numbers. And I'll open. Now, this is easy. But back to, forget just a second the zero knowledge aspect. I mean, we are talking about NP completeness. The verification of a proof, of a normal proof, mathematical proof, is a computational process. Computation is local. It proceeds by simple steps that check, the very simple objects, or if they, they just check that two things add up to a third, or things of this type. What Cook and Levin understood that you can take the verification process of proofs and convert them, the statement and the proof and the process, convert them to this language, let's say, of three coloring maps that are simple problems that capture all such processes. And locality of computation is what's essential in this translation. So they start from an abstract verification of a proof, and they generate from it this map, okay? That's what the algorithm does. Again, it's simple once you know what you want to do.
Okay.
It's a great idea and it's an amazingly powerful
Did these
tool.
guys win some prizes?
Of course, yeah, of course they did, and they should win more. Yeah. Yeah.
Have a proof. We might be quite difficult to find, like Fermat's last theorem took 350 years before my colleague in Oxford, Andrew Wiles, found the proof.
And of course, because it's the last one that anyone can prove, it's the most precious one. It's the one that's most desirable.